Most of us imagine the first human base near Mars, sitting where a Mars base belongs, on Mars. Pressurized rooms rest on red soil. Astronauts step outside under a dusty sky. The planet is under their boots. Now look above them. A tiny dark moon crosses Mars, and a few habitat windows glow along its shadowed rim. The first human foothold in the Mars system might cling to Phobos or Deimos. That sounds backward. You travel millions of miles to Mars, arrive beside it, and then refuse to land. But the idea has a practical pull. Carrying people and heavy equipment through the Martian atmosphere is difficult. Lifting them back into space requires another large machine with fuel and supplies. A crew heading for one of the moons could skip both jobs at first. They would still be local to Mars. From a nearby command post, they could operate robots on the surface without the long communication delay from Earth. Mars would fill much of their sky. The arrangement seems almost cheeky. Go all the way to Mars, then stop short of the ground. But an easier arrival may not mean an easier life. A tiny moon has almost no gravity and offers little natural protection from radiation. It also lacks the everyday advantages of having a large world under you. The mission hasn't removed difficulty. It has exchanged one kind for another. Whether that exchange makes sense depends on the future being built. Is this a temporary station for controlling machines, a stop for crews passing through, or the first step toward people living on Mars itself? Could Phobos or Deimos support that first step? Or would either moon leave the crew living just above the place they came to reach? If you enjoy exploring questions like this with me, subscribing helps others find them too. Liking and sharing the video helps even more. Now, let's begin. Suppose you laid every major part of a human Mars mission across a workbench. The long flight from Earth would take up plenty of room. So would the food, water, radiation shielding and life support. But two machines would dominate the table. One has to carry a heavy crew safely down to the Martian surface. The other has to lift them back into space. Those are very different jobs, and Mars makes both of them difficult. Its atmosphere is thick enough to create fierce heating during arrival, but too thin to slow a large spacecraft easily. A capsule can use a heat shield and parachutes to reach the ground. Heavy habitats and crew vehicles are another problem. They carry more mass, need more control, and can't simply drift toward whatever patch of ground happens to be available. They must arrive close to supplies and equipment that may already be waiting. Then, after months on the surface, the crew has to leave. That means bringing an ascent vehicle to Mars, keeping it healthy through the mission, fueling it somehow, and trusting it to work on the day everyone needs it. Every valve, engine and fuel line must survive the trip and the long wait. There is no rescue helicopter. A failure on the launch pad doesn't leave the crew inconveniently delayed. It leaves them on another planet. A mission to Phobos or Deimos removes those two surface transitions from the first human trip. The crew still travels through interplanetary space. They still enter the Mars system and remain there for a substantial stay. But their habitat doesn't have to plunge through the Martian atmosphere, and their return doesn't begin with a launch from the surface. You can think of it as crossing out two demanding operations on the workbench. No heavy human landing on Mars, no crew descent from Mars. The moons remain available as places to operate, observe and prepare while the surface stays below. Mars is still the destination. Its atmosphere and launch pad just aren't part of the crew's first visit. That specific advantage is why moon-first plans keep appearing in NASA studies of human exploration. Their strongest initial appeal isn't that Phobos or Deimos would be comfortable. They wouldn't be. It isn't that such a mission automatically costs less either. Once you count the spacecraft, supplies, power, communications and equipment needed around a small moon, the full comparison becomes much less certain. The narrower claim is solid. A moon-first architecture can send people into the Mars system without asking the first expedition to perform a heavy Mars entry, descent and landing. It can also bring them home without first launching them from Mars. That doesn't remove danger. It removes one class of dangerous operations from the opening attempt. For planners facing a thin atmosphere on arrival and a hard climb on departure, that is a serious attraction. If you can reach the neighborhood while skipping the hardest landing and the hardest return climb, why wouldn't you stop at one of the moons first? Because once you've decided to stop near Mars, the moons can seem almost embarrassingly reasonable. There they are, two small pieces of rock already circling the planet. Why build your own place to wait when Mars has apparently left two waiting rooms outside? Phobos makes the temptation especially easy to understand. It orbits only about 3,700 miles, or 6,000 kilometers, above the Martian surface. At that distance, Mars wouldn't look like a remote destination hanging among the stars. It would dominate the sky. From a dark, rocky rim, you might watch the planet fill half your view while robotic lights moved far below. That changes the role of the crew. They're no longer travelers passing Mars on their way somewhere else. They're in the Mars system, close enough to work around the planet without standing on it. Machines could descend while people remained above. Rovers, cargo vehicles and scientific equipment could work on the surface, with the crew nearby to supervise, adjust plans, and respond when something went wrong. The delay in radio commands would also be far smaller than it is from Earth. A rover that pauses beside an unexpected rock wouldn't need to wait through the long exchange between planets. The people guiding it would be in the neighborhood. Mars becomes less like a distant target and more like a work site across the road, although the road happens to be empty space. Both Phobos and Deimos offer that basic arrangement. A crew can remain close to Mars while staying outside its atmosphere. Supplies could gather around the moon. Vehicles could depart from nearby. Surface missions could go down without requiring every person, habitat, tool, and return system to make the same trip. And that separation has a practical appeal beyond any single mission. The outpost could become a place for crews to receive cargo, maintain equipment, coordinate robots, and prepare short trips toward Mars. People would still be working at another planet. They just wouldn't have to begin by placing their entire living system on its surface. You can see why the idea starts to sound less like science fiction and more like sensible project management. Keep the people at the local command post. Send the machines into the difficult places. Learn how the planet behaves before committing a crew to the ground. It's the sort of plan that can make a very ambitious mission sound suspiciously like a cautious day at work. But this isn't a smaller version of settling Mars. It's a different proposal. The crew wouldn't be living on a little Mars with gentler conditions. They'd be occupying a nearby outpost whose value comes from being close to the planet while remaining separate from it. And closeness by itself doesn't prove that either moon is the best place to build. It only explains the pull. From Phobos or Deimos, Mars is close enough to work around, study and reach. The moon becomes a perch beside the planet. A nearby perch, though, is not the same as an easy home. Once you remove the landing, it's tempting to draw one clean arrow toward Phobos and stop thinking. The moon sits close to Mars. The crew stays off the planet. The mission avoids the most violent part of arrival and the difficult climb back to orbit, on a whiteboard that can look almost settled. But engineers have a habit of asking where the arrows go next. In a 2021 strategic review, NASA examined possible places for crews and equipment around Mars. Phobos was one option, but it wasn't treated as the automatic winner. High Mars orbit could perform some of the same jobs without putting the crew on either moon. That includes serving as a base for observation, communication, and control of machines working below. The reason comes down to movement. Reaching the Mars system is only the first arrival. After that, every spacecraft still has to enter the right orbit, meet the crew, deliver cargo, depart again, and leave enough fuel and time for the return path. Choose a destination, and you also choose the web of routes attached to it. Think of avoiding a difficult mountain road by stopping at a railway station nearby. You've removed the worst drive. Good. But if every box, passenger and vehicle must then change trains twice, wait on separate platforms and follow different routes home, the station isn't free. The difficult part has changed shape. Phobos creates its own version of that problem. It travels deep in Mars's gravity and races around the planet in a low orbit. A vehicle arriving from Earth may not naturally pass through the exact path needed to meet it. Cargo, crew vehicles, surface landers, and return craft can each prefer different orbits. Bringing them together may require extra maneuvers, propellant, rendezvous hardware, and operational time. High Mars orbit may avoid some of those demands. A crew stationed farther out could meet arriving vehicles more easily under certain mission designs, then control robotic work on Mars without descending to Phobos first. That doesn't make high orbit superior in every plan. It means the comparison has to include the whole transport chain, not just the destination that looks closest on a diagram. There are other costs as well. Living on Phobos requires equipment to approach, anchor, and operate around a tiny body with extremely weak gravity. Staying in orbit replaces those surface problems with the demands of a long-lived orbital habitat. Neither choice comes without machinery, risk, or awkward procedures. They simply charge the mission in different places. So the Moon First idea still works as a serious proposal. Avoiding Mars entry and ascent remains a major advantage. NASA's review just removes the sense that proximity settles the argument. Low, close, and dramatic do not mean operationally effortless. A single arrow to Phobos soon becomes transfers, meeting points, fuel budgets, backup paths, and a route back to Earth. If the closer moon is not the automatic choice, which perch around Mars actually makes the most sense? Phobos is the moon that seems to answer before you've finished asking. It's larger than Deimos, closer to Mars, and familiar from decades of mission plans and imagined outposts. If you were choosing a place to watch Mars from, your eyes would probably go there first. And there's a physical reason for that pull. Phobos measures roughly 27 by 22 by 18 kilometers, or about 17 by 14 by 11 miles. It's a small battered object, shaped more like a rough stone than a round moon. Yet beside Mars, it feels less like a distant satellite and more like something caught just above the roof. Phobos orbits only about 6,000 kilometers above the Martian surface. That's around 3,700 miles. Our moon, by comparison, is roughly 384,000 kilometers from Earth, or about 239,000 miles away, so the view from Phobos wouldn't resemble the modest disk hanging over your backyard. Mars would occupy an enormous part of the sky. Its curved horizon, pale clouds, dust, and changing light would feel immediate. Then there's the speed. Phobos circles Mars in less than 8 hours. From the Martian ground, it rises in the west and moves rapidly overhead. From a base near Phobos, the world below would never feel remote or still. Mars would turn below you while the little moon swept around it again and again. Everything about the place would say nearby. Imagine standing near the rim of Stickney, the huge crater carved into one end of Phobos. The ground barely holds you. A careless jump would become a serious piece of mission planning. Beyond the crater wall, Mars fills the sky so completely that it seems almost touchable. You aren't peering across a dark gulf to world you came to study. You feel tucked against it. That physical intimacy creates a powerful command post instinct. A crew there could watch Martian weather develop, communicate with machines on the surface, and remain visibly connected to events below. Radios and screens would handle the actual information. Still, geometry has emotional weight. When your destination fills the window, distance feels conquered before the harder work has even begun. Phobos also looks like the brave choice. It gives us the image people expect from humanity's first foothold near Mars, a scarred little moon, a huge red world overhead, and astronauts working within sight of the place they came to explore. Deimos sits farther out and offers less visual drama. Phobos gets the better poster, and posters have a way of sneaking into engineering instincts. So the attraction isn't foolish, and it isn't merely better branding. Phobos keeps starring in Mars base plans because its closeness is real. You can see it in the scale of Mars overhead and feel it in the moon's rapid orbit. It offers the sensation of already being there. But that sensation can make closeness carry more authority than it deserves. A view may shape what a mission feels like, without deciding how the mission should be built. Phobos can be the moon that looks inevitable, while another orbit proves easier to live with. Inevitable and best are two different words. Deimos usually enters the conversation sounding like the spare. It's the smaller moon, the farther moon, the one that takes longer to go around Mars. If Phobos proves inconvenient, perhaps Deimos gets called in. That seems sensible until you notice that distance changes more than travel time. Deimos is a small, lumpy world, roughly 15 by 12 by 11 kilometers. That's about 9 by 7 by 6.8 miles. Its dusty surface looks smoother than Phobos, partly because loose material has softened the edges of many features. Mars still commands the sky, but it doesn't seem to swallow everything around you. Deimos feels less like a ledge above Mars and more like a separate place beside it. The slower pace changes the workday too. Deimos takes about 30 hours to complete one orbit of Mars. That is surprisingly close to the rhythm of a Martian day, which lasts a little more than 24.5 hours. From the surface, you wouldn't feel as though your workplace were racing around the planet every few hours. The geometry changes more gradually, which can make planning less frantic. Think of trying to work beside a moving lamp. Standing closer gives you more light, but it also makes every small movement of the lamp more dramatic. Step back, and the light is weaker, yet its angle may stay usable for longer. A moon's distance from Mars creates a similar trade-off. Closer isn't a universal advantage. It depends on what the crew is trying to see, when they need to see it, and how long the view must last. That becomes important if astronauts are controlling machines on Mars. Radio commands from either moon would arrive quickly enough for near real-time work. But the Sun, the Moon, the surface site and the spacecraft all keep changing position. A good operating period needs more than a short signal delay. The crew also needs power, visibility, and a communications path that isn't spoiled by darkness or an awkward alignment. Even a fast command is no help when the working window has closed. NASA's strategic review of human missions around Mars noted that Deimos can offer better illumination trade-offs for teleoperation than Phobos in some designs. That doesn't make Deimos the winner. It means the farther orbit may preserve a workable combination of sunlight and surface access when the closer moon becomes less convenient. Once you stop treating distance as failure, Deimos begins to sound surprisingly reasonable. It offers less closeness to Mars, but potentially calmer working geometry around it. That could suit a mission built around operating rovers, preparing landing sites, or studying the planet remotely. A crew whose main task is happening down on Mars may value dependable angles more than a dramatic view. So the choice between these moons can't be settled by asking which one hugs Mars more tightly. It depends on the job. If Phobos and Deimos each support a different kind of mission, what are the humans actually being sent there to do? That question opens a third option, and it doesn't have a surface at all. A crew could live in high orbit around Mars, circling the planet in open space, with neither Phobos nor Deimos under their feet. At first, that can sound like avoiding the decision. If people have traveled all the way to Mars, surely they should stand on something. A moon feels like a destination. An orbit feels like waiting. But those feelings don't tell us which place makes the better command post. NASA's 2021 Strategic Review compared both Martian moons with high Mars orbit. Orbit wasn't treated as empty space between the serious choices. It was one of the serious choices. The contest had quietly grown from 2 possible moons to 3 possible ways of keeping people near Mars. Think of a work crew repairing a building. They need somewhere nearby for tools, rest, and coordination. That place doesn't have to be attached to the building. A van parked across the street may do the job with less trouble than a temporary shelter bolted to the wall. High Mars orbit could work in much the same way. From there, astronauts would remain close enough to operate machines on Mars with little communication delay. Commands would arrive quickly. Camera views and instrument readings would return quickly. A rover could become something closer to a pair of distant hands, instead of a machine that must pause while instructions travel from Earth. The crew could also study Mars, manage supplies, wait for the right conditions, and prepare later missions. None of those jobs automatically requires boots on a small moon. Avoiding that surface also removes an entire set of chores. Phobos and Deimos have extremely weak gravity. Landing near either one means matching its motion, approaching carefully, and anchoring equipment that would otherwise drift away. Dust disturbed by people or machinery may behave badly. Habitats, power systems, and communication gear would all need to work on uneven ground whose details remain only partly known. An orbiting habitat has its own risks. It needs propulsion, radiation protection, dependable life support, and careful control of its path. It isn't the effortless choice, but it gives engineers a cleaner baseline, what is required simply to keep humans near Mars, before adding the burden of working on another world. That changes how the moons should be judged. Their closeness no longer grants them a free victory. Phobos must offer something worth landing and anchoring for. Deimos must do the same. A moon might provide raw material, scientific access, shielding, or a stable place for equipment. Later missions might gain advantages that an orbiting station couldn't match. Those possibilities remain open. Still, there's a mild absurdity in the comparison. After arguing over which piece of Martian ground should become humanity's first local perch, the sensible answer might be none of it. The habitat could simply keep falling around Mars, never landing anywhere. So if orbit can provide fast control, nearby staging, and a place to wait, what can humans on Phobos or Deimos actually do better? Imagine you're sitting inside a quiet, compact habitat above Mars. The windows show a rust-colored world turning below. Across the room, screens carry live views from rovers, drills, and sample arms on the surface. When an operator moves a control, the machine responds after a short local delay. It doesn't wait for a command to cross the space between planets. That difference changes the work. A crew near Mars wouldn't need to stand beside every machine to be physically useful. They could serve as a nearby command room, supervising a much larger robotic workforce below. From Earth, fluid control is impossible. Depending on where the planets are, a radio signal takes several minutes to reach Mars. The reply takes several more to come back. By then, a rover may already have met the loose rock, hidden ledge, or stubborn drill bit that made the original command a bad idea. So engineers give Mars robots careful instructions, then wait. The machines also need enough onboard judgment to stop when something looks wrong. Move the operators into the Mars system, and that burden becomes lighter. The robot can send back what it sees. A person can inspect the view, adjust the plan, and send another command while the situation is still current. You still wouldn't drive it like a car in the next room. Orbital position, blocked lines of sight, and relay paths would shape when direct contact was possible. But compared with control from Earth, the exchange between human and machine could become far more natural. NASA studies of human missions around Mars have treated this lower delay as a practical reason to send crews near the planet. The appeal isn't joystick entertainment, it's patient, demanding work. A geologist could guide a rover toward the part of an outcrop that preserves the most revealing rock. A sample arm could change course after its first scrape exposes an unexpected layer. If a wheel begins slipping, a nearby operator could respond before repeated attempts dig the machine deeper. The same arrangement could help with local resource work, usually called in situ resource utilization, or ISRU. Robots might search for water-bearing material, test processing equipment, move soil, or prepare supplies for later crews. When a machine jams or a sensor gives an odd reading, nearby humans could diagnose the problem through several quick exchanges. From Earth, that same repair might stretch across hours or days. There's something pleasantly workmanlike about this version of human exploration. The crew doesn't arrive and immediately pretend Mars is a new suburb. They stay above it, warm and protected, while machines handle the dust, cold, and heavy labor. A small group of people could lend human judgment to many robotic hands. That's a serious benefit. It may be the strongest practical case for putting humans near Mars before putting them on Mars. But usefulness doesn't settle the destination. Fast supervision explains why people might enter the Mars system. It doesn't yet explain why they should anchor themselves to either moon. That distinction is easy to miss. Once you see the value of nearby human control, a moon base can start to feel like the conclusion. Put the crew on Phobos or Deimos, give them a bank of screens, and let robots do the dangerous work below. It sounds sensible because it is sensible. It just doesn't finish the argument. NASA's own destination assessments were more restrained. They recognized teleoperation as a serious advantage, but said its applications still needed more study before it could become a primary reason for choosing a destination. Faster control could improve a mission without paying for the entire mission built around it. Think of choosing where to build a fire station. A shorter drive to an emergency is clearly better. But that alone doesn't tell you which block deserves the building. You still have to compare cost, access, safety, maintenance, and how often that location offers an advantage no other site can match. A real benefit may still fail to choose between two addresses. The same problem appears around Mars. A crew on a moon could send commands to a rover with very little delay, but a crew in a suitable high orbit could also communicate quickly. The command path would be much the same: astronaut, radio link, rover, reply. Put those paths side by side, and the difference is smaller than you might expect. An orbital station could move in and out of direct contact, and its changing position would affect operations. A moon offers a stable physical site, along with constraints of its own. The two options aren't interchangeable. Still, the timing advantage doesn't belong only to the moons. A 2021 strategic critique pressed this point directly. Low latency control, by itself, did not decisively favor Phobos or Deimos over high Mars orbit. That doesn't remove the advantage. It trims the claim to its proper size. The crew needs to be near Mars. Teleoperation alone doesn't tell us exactly where near Mars. Robots are changing the comparison too. A rover that needs a person to approve every careful movement gains a great deal from nearby supervision. A rover that can recognize hazards, plan a short route, and recover from routine problems needs less constant help. Human judgment still counts when something unusual happens. But as autonomy improves, fewer tasks require someone hovering over the controls, like a nervous driving instructor who can't reach the brake pedal. There's no fixed answer because both sides keep changing. Human control systems improve, robotic independence improves, communications networks improve. By the time crews arrive, some jobs that once demanded constant attention may need only occasional intervention. Teleoperation remains one of the strongest tools available to a crew near Mars. It can make surface robots faster and easier to rescue when they get into trouble. It just isn't a complete mission philosophy. To choose a moon, we need more than a short radio delay. We need to know what the crew gains from living on an actual place instead of circling above it. What kind of home would either moon provide? Calling either moon a home may be where the idea starts to wobble. A home is chosen partly for the life you can build there. Phobos and Deimos would be chosen for the work they let you do somewhere else. Their strongest role isn't as a suburb of Mars, it's as a command post hanging above it. That change sounds small, but it removes a lot of comfortable decoration. You don't need streets under glass, families arriving, or a settlement slowly becoming a town. Imagine a spare habitat instead. Workstations face a wall of surface maps. Communications equipment hums behind sealed panels. Outside the window, Mars fills much of the view. The moon under the habitat is less a world for building a new society than a platform holding the room in place. That may be the strongest case for sending people there. The crew could operate machines across Mars, study the planet and its moons, maintain nearby equipment, and respond when automated systems couldn't cope alone. Their value would come from being close, capable, and able to improvise. A human command room over Mars. But command rooms on Earth have doors. People finish a shift, stand up, and go somewhere that isn't part of the mission. A command post on Phobos or Deimos wouldn't offer that release. The crew might remain for months, perhaps longer. The duration would depend on the mission, and we shouldn't assume every stay would be brief. However long it lasted, The same small habitat would be office, kitchen, bedroom, clinic, shelter, gym, and emergency refuge. Then there's the work outside. Equipment would still need inspection. Antennas would jam. Seals, cables, instruments, and power systems would fail at inconvenient times. Someone would eventually have to put on a suit, leave the pressure behind, and step onto a surface with so little gravity that a normal push could send the body drifting in an unintended direction. Even walking would stop being the ordinary action your legs have practiced since childhood. That's where the romance gives way to knees, lungs, muscles, sleep, and fear. Mission diagrams can make an outpost look like a clean box connected to Mars by tidy lines. A crew would live through something less forgiving. Every drink would come from a managed supply. Every breath would pass through machinery. Exercise wouldn't be recreation. It would be an attempt to slow whatever a long stay in that environment was doing to the body. And after the suit came off, there would still be dust, noise, recycled air, interrupted sleep, and nowhere else to go. The moon-first idea becomes stronger when we stop asking whether either moon could become a second Earth. It doesn't need to. It needs to work as an operations outpost without slowly wearing down the people inside it. So once the maps and control screens are in place, what would a human body actually experience while living and working there? You might imagine the first person on Phobos stepping outside much as the Apollo astronauts did. One careful boot comes down, the other follows. Then comes an awkward hop across the grey soil, with Mars filling half the sky. But Phobos would barely hold you down. Its surface gravity is about 0.06% of Earth's gravity. Not 6%, 0.06%. You would still have weight there, but so little that ordinary walking would stop making much sense. On Earth, each step works because gravity returns your foot to the floor. Your body falls forward slightly. Your next foot catches you, and the rhythm continues without much thought. Even on our moon, where gravity is 1/6 of Earth's, astronauts could hop because they came down quickly enough. Their movements looked strange, but the ground still set the rhythm. Phobos is different. Push against the surface, and you may spend a long time waiting for it to meet you again. A suited astronaut attempting an energetic Apollo hop could rise into a slow, useless drift above the dust. You wouldn't fly away forever. You might simply float high enough and long enough to regret the enthusiasm. That changes almost every movement. You couldn't trust body weight to keep a drill steady. Turning a stiff valve could twist you instead. Pulling a cable might send you backward. Swing one arm too quickly and the rest of your body would answer. If you stumbled, you wouldn't hit the surface very hard, but recovering could become an absurdly slow performance. Lifting yourself would be easy. Stopping yourself would take practice. Inside an outpost, you'd probably move by holding rails, slipping your feet into restraints and pushing gently between fixed points. A coffee cup wouldn't stay on a table simply because the table had legs. Tools would need clips. Your hands would need somewhere firm to brace before doing serious work. Outside, tethers and handholds would matter more than any heroic pair of boots. Dust underfoot would make the place look like solid ground, while your body kept finding out otherwise. The experience would be less like crossing a landscape and more like working around the outside of a space station covered in dirt. It still wouldn't be exactly like floating inside a space station. Phobos has gravity. Loose grains settle. An object released carefully will fall toward the surface. Its weak pull also shapes motion in ways that free-floating does not. But for the ordinary business of living and working, this would count as microgravity. And then there's Mars. It would hang enormous overhead as Phobos raced around it. You could stand under that sight only in the loosest sense. More likely, you'd be clipped to the moon, one glove around a rail, trying not to turn a simple reach into a slow departure. A Phobos outpost would be a space station with dust underfoot. The surface would be real. Its gravity would simply be too weak to organize your body around it. Once you're clipped to the surface, staying there becomes part of every job. Careful practice would help, of course. Astronauts get very good at moving slowly and planning each reach. but practice can't give your body the weight it no longer has. Think about using a geology hammer on Earth. Your boots press into the ground, your legs brace your hips, the ground pushes back while your arm swings. Most of that happens without thought. On a tiny moon, the hammer still meets the rock, but your body has almost nothing holding it down. The blow can move you as readily as it moves the tool. Even gentler work has the same problem. Twist a drill and the drill twists back. Pull a sample from a stubborn crack, and you pull yourself toward the crack. Tug on a cable, and something at the other end may begin drifting too. A tool, a tether line, and a suited astronaut can all end up pulling against one another very slowly, with all the dignity of 3 people losing an argument with a garden hose. That slow motion isn't harmless. A person who slips won't fall far in the usual way, but may rotate beyond reach of a handhold. A tool released with a small push can travel long enough to interrupt the job or disappear from the work area. Equipment that starts moving may need to be caught without giving the person catching it a new unwanted motion. NASA mission studies have treated this as a basic architecture problem. Their designs have examined anchors driven or attached to the surface, handholds placed around work areas, restraint points for tools, and booms that carry an astronaut outward while keeping the body connected to a stable structure. Specialized excursion vehicles could provide both transport and a base to work against. The vehicle wouldn't merely take you somewhere, it would help keep a surface below you. This means the suit and the science tools are only part of the worksite. Before someone drills, collects, repairs, or lifts, there has to be a chain of restraint. The astronaut connects to an anchor. The tool connects to the astronaut or the platform. Loose equipment gets secured before another item comes free. Movement becomes a sequence of attachments, releases, and checks. Engineers already have workable ideas for each piece. Tethers, rails, foot restraints, robotic arms, and maneuvering systems are familiar hardware. The difficulty is deciding which combination can support hours of real fieldwork without turning every sample into a small rigging operation. And that choice reaches into the whole mission. More anchors mean more mass to carry. More restraint steps mean more time in the suit. Awkward bracing increases fatigue. A scientist may be able to reach a rock, yet spend most of the effort arranging a body, a tool, and a vehicle so the rock can actually be touched. On these moons, mobility and work can't be separated. The hardware that keeps an astronaut from drifting away also decides how much science gets done before it's time to go inside. After all that drifting, anchoring, and careful bracing, Mars begins to look almost ordinary. It isn't ordinary, of course. Step outside without protection and you would meet thin carbon dioxide air, bitter cold, radiation, and dust that finds its way into everything. But once you've arrived and built a safe place to live, Mars gives the body something the moons cannot. It gives you a floor. On Mars, boots press into the ground and stay there. A dropped tool falls. You can lean into a shovel, push a cart, or set a sample beside you without attaching each object to something else. Mars has about 38% of Earth's gravity. That's weak enough to change how you walk and how your body ages, but strong enough to restore the basic direction of daily life. Down is down again. You'd probably move with a longer, lighter stride. Lifting supplies would feel easier. A person weighing 180 pounds on Earth would press on the ground as though they weighed about 68 pounds. That's roughly 82 kilograms, producing the ground force of about 31 kilograms on Earth. Your mass wouldn't change, so a heavy crate would still resist when you tried to start or stop it. It could still knock you over if it moved badly, but your body would no longer need a tether just to remain near the workplace. The clock would feel familiar too. One Martian day, called a sol, lasts about 24 hours and 39 minutes. Earth gives us 24 hours. Mars adds only 39 minutes. Your sleep cycle would need some adjustment, and those extra minutes would accumulate against Earth clocks. But morning, afternoon, evening, and night would still arrive in a rhythm the human body can recognize. Meals could follow days. Work shifts could end at something that feels like bedtime. Even the simple act of getting tired after sunset would belong to a cycle close to the one your body already knows. That doesn't make Mars comfortable. Its partial gravity may still weaken bone, muscle, balance, and the heart over long stays. We don't yet know how well a human body can remain healthy for years at 38% gravity. Mars merely offers a more planet-like kind of hardship. You live inside shelters and suits, but ordinary actions still behave much as your brain expects. Phobos and Deimos make a different bargain. Reaching their surfaces avoids some of the hardest demands of landing on Mars itself. Once there, though, many burdens of free space remain. Bodies drift, tools wander. Dust doesn't simply settle under your feet. Every outdoor task begins with the problem of staying attached, and every habitat must support people whose bodies receive almost no help from gravity. So the choice tightens into something very human. The moons may offer an easier arrival, followed by stranger daily life. Mars demands a harder arrival, then gives you a world where walking, working, sleeping, and setting down a cup make more sense. If living on the moons is this awkward, do they at least repay the trouble by protecting the human body from one of spaceflight's greatest harms? It's easy to hear habitat near Phobos and imagine the moon sheltering everyone nearby. Phobos is a solid rock more than 13 miles across, about 22 kilometers. Surely that much stone must help. It can, but only when the stone is actually in the way. Think about standing beside a brick wall during a rainstorm. The wall protects you from rain coming through the bricks because the bricks stop it. Step beyond one corner though, and most of the sky opens again. You're still close to the wall. You might be close enough to touch it. But closeness isn't what keeps you dry. The wall has to stand between you and the rain. A habitat orbiting beside Phobos has the same geometric problem. The moon blocks radiation arriving through the patch of sky covered by its body. From every other direction, the habitat remains exposed to space. Being close sounds protective. The open sky says otherwise. NASA examined this distinction in a 2014 study of possible human missions around Mars and its moons. The researchers estimated that a habitat orbiting close to Phobos would receive only a modest reduction in radiation exposure. The moon would block part of the incoming environment, but not enough to remake the crew's health risk. A large rock outside the window is still only covering one part of the window. Now place that habitat against the surface. A large mass of rock suddenly fills much more of the crew's surroundings. The moon sits below them, close and solid, removing a broad section of exposed sky. Set the habitat partly into the ground, or cover it with local material, and more mass stands between the crew and radiation arriving from above. Phobos hasn't acquired any special shielding power. The crew has simply put the rock where it can do some real work. That's the physical dividing line. Beside the moon is not the same as behind it. A free-flying station near Phobos may still gain operational advantages from staying close. Crews could reach the surface quickly. They could control nearby equipment without the long communication delays that complicate work from Earth. They could use the moon as a staging point for other missions. But none of those advantages turns open space into a wall, and none changes which directions remain exposed. A surface-integrated habitat changes the health story for the people living inside because it makes Phobos part of the protective structure. The moon's bulk becomes something the crew can shelter against. Even then, Phobos doesn't become a completely safe haven. Radiation can still arrive from the exposed sky, and the habitat would still need shielding of its own. This is relative protection, not immunity. So the important choice isn't simply whether people go to Phobos, it's exactly where they live after arriving. Put the habitat nearby, and the moon is mostly a destination outside the window. Put the habitat against it, and part of Phobos becomes a wall. You can see the difference on a mission board before anyone feels it inside a habitat. Start with the Mars orbit mission as the full-length bar. Then add a habitat circling Phobos from about 20 kilometers away, roughly 12 miles. Its radiation bar is shorter, but only just. In the study, that distant retrograde orbit reduced the crew's radiation exposure by about 4 to 6%. 4 to 6% is real. Engineers wouldn't throw it away. But it's also small enough that you might miss the change at a glance. Moving the habitat near Phobos did not turn the Moon into a major shield. From that orbit, the crew still has open sky in almost every direction. Phobos blocks radiation arriving through the small angle covered by the Moon. Most other directions remain exposed. Imagine standing several steps from a narrow wall during a rainstorm. The wall helps when the rain comes from behind it. Rain arriving from anywhere else still reaches you. Distance leaves much of the wall's possible protection unused. Now move the habitat down to the surface. Set it against the Moon, where Phobos fills far more of the space below and around the crew. In the same study, the reduction reached as high as 34% compared with a Mars orbital mission. That's 34%. On the mission board, the second bar is plainly lower. What looked like a minor choice of address has become a serious design decision. Phobos hasn't changed. The habitat has committed to using the Moon's mass. Across the mission, a larger share of the surrounding radiation meets rock before reaching the crew. The exposed sky still contributes radiation, and the habitat still needs protection of its own, but surface placement puts far more rock between the living space and part of the radiation environment. The architecture is finally taking advantage of the Moon instead of merely traveling beside it. These figures came from one study using particular mission designs. They aren't permanent guarantees for every Phobos habitat. Change the orbit, mission length, building materials, solar conditions, or the way the living areas meet the surface, and the result may change. The study found a reduction of up to 34% within that architecture. It did not award every future surface mission the same automatic discount. Mars can provide stronger natural shelter when crews use thick soil, deep trenches, caves, or lava tubes. A small moon cannot match the mass of a whole planet. Phobos offers something narrower. If the habitat hugs the surface, the Moon can remove a substantial share of exposure. If the habitat stays nearby, most of that possible shelter remains out of reach. So near Phobos and on Phobos sound like neighboring choices only in ordinary conversation. For the crew, they produce very different surroundings. One design gained a modest reduction of about 4 to 6%. The surface design reached as high as 34%. The protection came from where the habitat was placed, not from having Phobos written on the mission plan. 34% is enough to change a mission. It is not enough to change the ranking. Phobos does win something important. A habitat pressed close to its surface can put rock between the crew and part of the radiation around them. NASA's public description of a possible moon base makes the same basic case. For much of each orbit, the base would have the Moon's rock on one side, blocking particles that would otherwise pass through open space. Think of standing under a concrete awning during a storm. It doesn't stop every drop coming from every direction, but it removes a large part of the sky from the problem. On Phobos, the overhead mass would be rock rather than concrete, and the storm would be radiation rather than rain. The shelter is real because the mass is real. That makes a surface base on Phobos better protected than a comparable habitat floating nearby. It may also make long stays easier to justify than missions conducted entirely in open orbit. The crew gets local shielding without carrying every kilogram of it from Earth. On a mission where every kilogram must be launched, moved and supported, borrowed rock is a serious advantage. There's another benefit too. The protection doesn't depend on a machine staying active. Pumps can stop. Power systems can fail. Rock continues being rock. It cannot block radiation arriving through the exposed part of the sky, but the portion it does block requires no fuel, maintenance, or spare parts. For a crew far from Earth, passive protection has value of its own. But Mars still sits below, with far more material between a crew and space. It is a planet with a large body of rock and an atmosphere. Neither makes its surface harmless. Mars has no strong global magnetic field, its atmosphere is thin, and crews would still need shielding built into their habitats. Even so, the 2021 strategic critique kept Mars itself as the stronger local shelter benchmark. Phobos can cover part of the sky. Mars supplies the ground, the bulk of a planet, and some atmospheric protection as well. So the comparison depends on what the mission is trying to avoid. If planners want crews near Mars while postponing the hazards of landing on the planet, Phobos becomes attractive. You can gain meaningful shelter and remain outside the hardest part of a Mars arrival. That is where the Moon makes its strongest health case. If the aim is simply to find the best natural protection available in the Mars system, the planet remains ahead, not perfectly protected, not safe in any casual sense, just better supplied with the mass that radiation shielding requires. The clean ranking is this: a Phobos surface habitat can be much better than free space. Mars can still provide stronger natural shelter than Phobos. The Moon's advantage belongs to an architecture that values staying off the planet, not to a claim that the Moon protects people better than the planet does. And once a crew presses its habitat against Phobos to gain that rock overhead, what happens when the Moon's dust comes indoors with them? You might expect the dust problem to be easier on Phobos and Deimos. In one important way, it really is. Mars has an atmosphere. It's thin, but there's enough air to make weather. Winds cross the surface, lift fine grains, and carry them far beyond where they started. Sometimes the dust spreads until much of the planet sits under a rusty haze. A crew may prepare for local conditions and still have a storm arrive from somewhere beyond the horizon. Nothing like that happens on either moon. Phobos and Deimos have no atmosphere to push against loose material. No air means no wind, and no wind means no advancing wall of dust, no regional weather system coating equipment, and no planet-wide storm dimming the daylight for weeks. Look across the horizon from a moon habitat, and the view would remain still. There would be no clouds gathering in the distance, no dust fronts swallowing the ground, almost nothing we'd recognize as a sky. The black above you would simply meet the surface at a sharp edge. That stillness removes an entire family of planning problems. On Mars, a surface crew has to account for changing visibility, dust driven into exposed machinery, and sunlight weakened across huge areas. Solar power can fall just when heaters, pumps, and life support equipment must keep running. Routes may become harder to follow. Work outside can be delayed by weather that began hundreds of miles away. A base on Phobos or Deimos wouldn't face those Mars-scale storms. Its solar panels wouldn't be covered by dust arriving on the wind. A vehicle wouldn't meet a moving cloud of grit on the way home. Mission planners could leave storm forecasts out of the daily schedule. In a place already full of awkward problems, removing even one unpredictable threat would matter. Equipment could still become dirty, of course. Seals, joints, radiators, visors, and solar panels would still need protection from loose grains. But crews wouldn't have to prepare for an atmosphere capable of picking those grains up across a broad region and delivering them to the base. The source of the dust would be nearby. That difference could make inspection, cleanup, and scheduling more manageable. This is a real advantage. It shouldn't be brushed aside merely because the moons have other problems. Mars and its moons do not share the same dust environment. The missing atmosphere genuinely makes some surface operations simpler. So you can relax, at least briefly. There is no Martian storm wall coming over that silent horizon. But the absence of wind doesn't make the ground clean. It only tells us which force is missing. Dust can still be struck, kicked, charged, and thrown. With almost no gravity and no air to slow a moving grain, small disturbances can produce consequences that weather on Mars does not. The moons escape dust carried by storms. What remains is dust moved by impacts, machinery, electric charge, and the crew itself. The horizon is calmer than Mars, but the ground below it may be much less settled. Imagine lowering a spacecraft toward Phobos. The engines fire, and the ground below seems to exhale. A pale cloud lifts around the landing site, but it doesn't billow like smoke, because there's almost no air to shape it. It spreads as countless separate grains, each following its own slow path through weak gravity. On Earth, a boot scuffs the ground and the dust drops nearby. On these moons, the same movement can send a grain much farther than your body expects. Phobos has less than 1/1000th of Earth's surface gravity. Deimos has even less. A small push that means nothing here can become a long, slow flight there. You move your foot, then watch the ground refuse to settle in the familiar way. In 2021, a NASA strategic review examined this problem for missions around Phobos and Deimos. It warned that surface material disturbed by a kick or a thruster plume could enter paths that carry it around the Moon, or even away from it. That doesn't mean every grain becomes a permanent satellite. Most won't. The warning is about how easily ordinary operations can give some particles enough motion to stop behaving like nearby dirt. So the dust hazard isn't waiting for a storm. It arrives with the spacecraft. A landing engine can throw material across the site before the vehicle has touched down. An anchor driven into the surface can release another spray. A boot, a tool, or a wheel can add smaller clouds. With no thick atmosphere to slow them, the grains keep moving until gravity, another surface, or a piece of equipment interrupts their path. On these moons you may become the weather, though the result is eerier than weather, a silent cloud whose individual grains follow paths your body was never built to judge. Deimos offers evidence that this movement adds up. Its surface carries a dusty layer made partly from material thrown out and later deposited again. Over long periods, grains can leave one place, travel under the Moon's weak pull, and settle somewhere else. The surface you meet may contain dust delivered from well beyond the patch under your feet. That changes how landings and surface work fit together. Thrusters can contaminate instruments before they begin measuring. A drifting cloud can reduce visibility when a pilot or navigation system needs the ground most. Grains can coat radiators, lenses, seals, or sampling equipment. Material thrown during one operation may settle onto a different site later, mixing locations that scientists hoped to study separately. And because the cloud is self-made, avoiding it takes more than choosing calm conditions. Engine direction, landing distance, anchor placement, and even where people move become part of dust control. There is no forecast to wait out. The disturbance begins when you arrive. Phobos and Deimos may offer a sky without storms. Yet every landing writes a brief new set of particle paths across that sky, and some of the dust you meet later may be dust you threw yourself. It's tempting to give the dust its own engineering box. Put filters on the air system, cover the lenses, brush the suits, then let the mobility team worry about boots, anchors, tethers, and handholds. But on these moons, those boxes share a wall. You can see the connection in one crew member drifting a little too far from the worksite. A tether tightens and stops the motion. Good, the person is safe. Yet the pull must end somewhere, perhaps at an anchor driven into the ground. That anchor presses against loose material. The tether loads it from the side. Grains shift, scrape past one another, and some break free. The same action succeeds and causes trouble. Weak gravity sits behind both results. It makes a person difficult to hold against the surface, so every small correction needs something firm to push or pull against. It also gives disturbed grains very little reason to come back down. A movement that would produce a brief puff on Earth can send particles along slow, extended paths here. Even standing still takes part in the exchange. A boot or restraint must apply force to keep the body in place. Braking requires force, turning requires force, setting a tool against a stubborn bolt sends force back through the worker and into whatever holds them down. Each force helps control a body, a vehicle, or a piece of equipment. Each one also reaches a surface made of material that may be barely settled. So mobility and contamination control aren't two problems that happen to occur nearby. They are two views of the same contact. If we follow the crew member, we ask whether the anchor held, the tether stopped the drift, or the vehicle turned safely. If we follow the grains, we ask what came loose, how high it traveled, and where it will settle. Pre-deployed equipment could make that contact gentler. Before the crew arrives, a robotic system might place prepared work platforms, fixed handholds, covered routes, or anchors designed to spread their load. Vehicles could use several contact points instead of digging sharply into one patch. Tools and restraints could be arranged so workers make fewer large corrections. Those choices can reduce the disturbance, They cannot make movement independent of it. The platforms still rest on the Moon. Anchors still transfer loads into the ground. A crew member who slips will still need to be caught, and the catching force still has to go somewhere. That hidden connection changes how the whole surface site must be laid out. A route isn't good merely because people can cross it. It must also limit what their passage throws toward habitats, radiators, instruments, and untouched sampling areas. An anchor isn't successful merely because it holds. Engineers must also ask what setting and loading it does to the ground around it. And if such gentle movements can become a coupled problem, what happens when a spacecraft has to land there, then push away again? At first, this part seems like a relief. A moon only a few kilometers wide can barely hold onto a spacecraft. Its gravity is so weak that landing should take little fuel, and leaving should be almost effortless. The raw energy numbers really are that friendly. Launching from Mars means climbing away from a world with serious gravity. A vehicle must accelerate for several minutes, carry a large propellant supply, and fight its way up to orbital speed. A tiny moon presents no comparable wall. A modest push can send a lander away from the surface. In propulsion terms, the difference is enormous. That advantage is genuine. It's one reason missions to small bodies can sound wonderfully simple. You don't need a towering ascent vehicle. You don't need the same engines, tanks, or fuel margins demanded by Mars. If all you're measuring is the change in speed needed to arrive and depart, the delta V, the tiny moon, wins easily. The fuel ledger looks merciful. But low energy and easy handling aren't the same thing. Think of moving an empty cardboard box across a table. It takes almost no force. And that sounds convenient until you need to place it on one exact pencil mark while a fan is blowing nearby. Because the box offers so little resistance, every small push counts. Your hand doesn't need strength. It needs restraint. A lander approaching a tiny moon faces a similar split. Weak gravity reduces the thrust needed to slow down or rise away. It does nothing to tell the spacecraft exactly where it is. It doesn't remove errors in the moon's shape, spin, surface slope, or local gravity. And it doesn't make contact with the ground harmless. An engine pulse that would barely adjust a vehicle near Mars might produce a noticeable change here. A landing leg can touch first and start the craft rotating. A rebound that would be trivial under stronger gravity may lift the vehicle clear of the surface. Even the exhaust used for a gentle descent can disturb loose material below the lander. None of that demands a powerful engine. It demands accurate sensing, careful timing, and a vehicle able to correct without overcorrecting. So the propulsion system may have an easy job in one sense and an awkward job in another. It doesn't need to deliver much force. It must deliver very small amounts of force at the right moment, in the right direction, without turning a soft arrival into a slow-motion bounce. Departure has the same strange character. Escaping the moon may require only a brief burn, yet that burn begins while the spacecraft is close to an irregular surface, surrounded by equipment, disturbed soil, and perhaps people. Too little thrust leaves the vehicle lingering where another contact is possible. Too much thrust can send debris outward or spoil the intended path. Mars makes you pay heavily for every kilogram you lift. A tiny moon forgives that bill. What it doesn't forgive is clumsy control. The energetic wall is low. The target for every movement is narrow. You might expect careful piloting to solve the rest. Approach slowly, lower the legs, and stop when they touch. That works when the ground pulls back with enough force to settle the vehicle. On a tiny moon, the ground barely helps. A better description is docking with terrain. Imagine bringing two objects together in space. You don't want them to collide, even gently. You want their motion relative to each other to reach almost zero at the instant of contact. A lander approaching Phobos or Deimos faces a similar problem, except one object is a spacecraft and the other is a lumpy, dusty moon. And unlike a docking port, the moon has no convenient ring waiting to catch you. The surface may slope. The local pull may change with position because the moon isn't round. Its rotation also affects how the lander moves nearby. NASA assessments of operations around these moons treat that local motion as a real navigation and control problem. Slow doesn't automatically mean stable. On Earth, weight presses landing gear into the ground. Friction can then help stop sideways motion. If a foot slips or a shock absorber pushes back, gravity quickly brings the vehicle down again. Weak gravity removes much of that settling force. The same springiness in a landing leg can now produce a bounce that lasts far longer than your instincts expect. So imagine the lander arriving only a little too firmly. One foot touches first. Dust moves outward. The leg pushes back, and the vehicle rises instead of settling. It may rise very slowly, perhaps slowly enough to look harmless, but it's moving again. Now the control system has to arrest that drift without driving another foot into the surface or blowing more material across the landing area. A small sideways motion can be just as troublesome. With little weight on the feet, the lander has less grip. An uneven contact may tip it, rotate it, or leave it floating a short distance above the place where it was meant to stay. A sensor may still be sorting out whether contact has ended while the lander is already moving away. None of this requires a violent impact. Tiny disturbances remain important because the moon supplies so little restoring force. Dust joins the problem at the point of contact. A thruster correction can disturb the surface. A bouncing foot can throw grains outward. Those grains may interfere with sensors, mechanisms, nearby equipment, or the next attempt to settle. Then departure repeats the interaction in reverse. The vehicle must separate cleanly without scraping, tipping, or sending its exhaust where it shouldn't go. This doesn't mean every touchdown turns into a drifting cloud of machinery. Good guidance, landing gear, sensors, and thruster control can manage it. But they have to be designed for a place where touching down doesn't guarantee staying down. That is why the cheapest part may be reaching the moon's surface. The expensive part is making contact so softly and with such control that the spacecraft can trust the ground under its feet. You might expect one clever lander to settle the problem. Give it better legs, gentler engines, and enough fuel, then use the same basic machine every time. After a few rounds of engineering, the awkward parts should disappear into one dependable design. But when NASA studies how people might work around these moons, the drawings don't converge on one vehicle. They split. Imagine opening a drawer marked Moon Mission and discovering several drawers behind it. One holds a taxi that carries astronauts between an orbiting base and the moon. Another holds a habitat delivered before the crew arrives. Another contains a long boom, keeping the main spacecraft at a distance while an astronaut or tool reaches toward the surface. Then there are pressurized excursion vehicles built to let people travel and work without treating every outing like a walk from a front door. These aren't cosmetic differences. They change where the crew sleeps, where fuel waits, what touches the ground, and how an astronaut reaches the thing they came to study. They also change which failure the mission is best prepared to survive. On Earth, you can decide where to park and then choose a ladder. Here, the ladder may decide the spacecraft. A pre-deployed habitat gives the crew a protected place to live, with supplies waiting when they arrive. But it has to land safely, start working on its own, and remain healthy before anyone is there to repair it. If it settles in the wrong place, the crew may inherit a long and difficult commute. A taxi keeps the larger living quarters away from the surface. That protects equipment that doesn't need to make the trip down. Yet every transfer adds docking, navigation, fuel handling, and another vehicle whose failure could leave people on the wrong side of the gap. A boom avoids placing the whole craft on uncertain ground. The spacecraft can hover nearby or hold its position while the boom reaches out. But now reach, stiffness, motion, and control become central to the mission. A pressurized excursion system gives astronauts more freedom and more time away from the main habitat, while adding mass, power demands, and machinery that must be carried across an enormous distance. The designs branch because surface operations shape the mission from the beginning. Habitat placement and the way astronauts leave the vehicle can't be added after the spacecraft is mostly finished. Change either one, and the vehicle's fuel plan, landing method, and emergency options change with it. That branching isn't failure. It's evidence that several compromises remain possible, with no obvious winner. Keep the habitat away, and transportation grows harder. Put it near the work, and landing becomes more demanding. Limit direct contact, and reach becomes a problem. Allow wider movement, and the excursion vehicle becomes a small spacecraft of its own. So these moons aren't a solved stop on the way outward. They're a family of competing mission plans: taxi, boom, habitat, excursion craft, or some combination that hasn't earned everyone's confidence yet. Once you see how much machinery may be needed simply to arrive, work, and leave, what prize on those difficult little worlds could justify all this trouble? At first glance, the answer may seem a little disappointing. After building taxis, booms, habitats, and excursion vehicles, you arrive at a pile of dark dust. No forests, no rivers, nothing that looks especially valuable. Just two small moons that have spent billions of years being treated as background scenery around Mars. But take a scoop of that dust and hold it under laboratory lights, and the whole argument changes. The regolith isn't merely dirt waiting to be pushed aside. It may be an archive box. NASA describes Phobos and Deimos as dark, carbon-rich bodies. That alone makes their materials scientifically interesting. Carbon-rich asteroids preserve chemical clues from the early solar system, including compounds that formed before planets settled into their present shapes. The Martian moons may carry some of that old material too, though their exact origins remain unsettled. Their surfaces may also contain ice-bearing material. We don't yet know how much, where it sits, or how accessible it would be. The evidence is enough to justify looking, but not enough to draw a treasure map, and the most revealing grains may have nothing to do with future fuel or drinking water. Think of the surface as an old carpet in a busy house. Dust falls onto it from several rooms. Tiny objects are tracked across it. A dropped crumb may tell you something about dinner, while a speck of soil may have come in from outside. Given enough time, the carpet holds a mixed record of what happened around it. Phobos and Deimos have been collecting their own version of that record. Their regolith contains material from the moons themselves, altered by radiation and countless small impacts. Some grains may also have come from Mars. A large impact on the planet can throw rock high above the atmosphere. Part of that debris may eventually reach a moon and remain mixed into its surface. That possibility gives scientists access to pieces of Mars without descending through the atmosphere, landing on the planet, and climbing back out again. The grains won't arrive with tidy labels. Researchers would still need to determine what came from where, and nobody can promise that every desired chapter of Martian history is sitting within reach of the first scoop. Japan's Martian Moons exploration mission, known as MMX, is built partly around this archive value. Its planned sample return from Phobos is meant to help scientists test how the moon formed and what its material records about the region around Mars. A small container of regolith could carry evidence about impacts, migration, surface weathering, and the early ingredients from which small worlds formed. So the first prize may be knowledge. That can sound modest beside visions of mines and permanent bases, but it changes how we look at these moons. A warehouse is valuable because we already know what we can remove from it. An archive is valuable because its ordinary-looking dust may preserve events we can no longer observe. Phobos and Deimos may be poor places to live, yet remarkably good places to remember. Once a place starts sounding valuable, it's easy to furnish it in your mind. Tanks on the surface, pipes running into processing units, a spacecraft arriving nearly empty and leaving with full propellant tanks. Phobos becomes a service station above Mars, while Deimos waits farther out with more supplies. There is a real idea behind that sketch. NASA has described these moons as scientifically interesting bodies that may contain carbon-rich material and other resources worth investigating. Their weak gravity could also make moving material away from the surface less costly than launching it from Mars. None of that is imaginary. It's enough to justify serious study. But finding a promising ingredient isn't the same as having a working supply chain. Suppose someone tells you there's water in the soil under your house. Before you call it a reservoir, you'd want to know how much is there, how deeply it's buried, whether it can be pumped, what else comes up with it, and how much energy the whole process consumes. A chemical signal tells you something is present. It doesn't tell you whether an industrial system can collect and use it reliably. That gap is especially wide on Phobos and Deimos. We still need better measurements of what their surfaces contain, how those materials vary from place to place, and how the loose regolith behaves when disturbed. Then come the engineering problems. Machinery has to grip the ground in very weak gravity. Dust has to be contained. Material has to be gathered, heated or separated, stored and transferred without drifting away or damaging equipment. Every step needs power, mass, time and hardware. A 2014 NASA study of human exploration around Mars did examine the value of operating from the moons. One strong case involved astronauts near Mars remotely controlling machines on the planet, including systems that could use local Martian resources. The short communication delay would let a human operator guide equipment with far more control than someone working from Earth. That study supports the moons as possible operating posts. It supports teleoperated resource work on Mars. It does not by itself show that Phobos or Deimos can provide propellant at an industrial scale. The location and the resource source are easy to blend together in a hopeful drawing. Engineering doesn't get that luxury. Perhaps later missions will find deposits that are concentrated, accessible, and worth processing. Perhaps one moon will prove far more useful than the other. We don't have enough close measurements or extraction tests to dismiss those outcomes. We also don't have enough to design a dependable fuel economy around them. So the cautious answer still leaves room for ambition. Phobos and Deimos may offer useful material, and they may become valuable bases for work around Mars. Today, though, they are resource candidates, not proven fuel depots. Presence is a clue. Maturity has to be built and demonstrated. From a distance, Deimos looks almost gentle. Its small, uneven plains are muted by powder, with the powder softening sharper features, but that calm surface may hide an extraordinary depth of loose material. NASA estimates that the regolith on Deimos could reach about 328 feet deep. That's roughly 100 meters. This is an estimate, not a measurement from a drill. Still, the possibility changes how you see this little moon. On Earth, 100 meters could bury a 30-story building. On Deimos, much of that depth may be dust. It didn't arrive all at once. Impacts strike the surface and throw fragments upward. Deimos has so little gravity that some debris escapes. Some takes slow paths above the moon, then settles somewhere else. Over immense spans of time, repeated escape and return may have helped build the blanket we see now. That makes the regolith more than leftover rubble. It may hold a long record of impacts, movement, and redeposition around Mars. Deeper layers could preserve older material below grains disturbed more recently. Taken together, those layers may reveal what struck Deimos and how debris traveled through this part of the solar system. A plane that looks nearly blank may contain a history written grain by grain. Now imagine placing a machine on it. Your foot can tell firm ground from loose sand almost immediately. A lander doesn't have that instinct. Its legs, anchors, wheels, drills, and sampling tools must be designed before they arrive. Engineers need some idea of how far each part will sink, how the grains will shift, and whether a movement in one place will disturb the ground nearby. If the surface gives way more than expected, a stable platform can tilt. If the grains cling, flow, or compact in surprising ways, ordinary tasks become difficult. A wheel might dig in where another rolls easily. An anchor might hold in one patch and slip in the next. Even taking a clean sample could mix the layers that made the site scientifically valuable. None of this means Deimos is unusable. Deep regolith might support some activities and complicate others. Its bearing strength could vary across the moon. The upper surface may behave differently from material farther down. We haven't tested enough of it up close to turn an estimated depth into a construction plan, a mining plan, or even a confident landing rule. The same grey powder could therefore be a scientific archive, an engineering problem, and material that people may someday learn to handle or process. Its value depends on what it contains. Its difficulty depends on how it behaves. Its strategic role depends on what a mission needs. Those questions meet in the same ground, but they don't share one automatic answer. Deimos leaves us with a specific unknown, perhaps 328 feet or 100 meters of displaced history below a surface that may not hold equipment the way engineers expect. If reaching Mars means learning to work carefully on unfamiliar ground, could beginning with a small moon still make the larger journey easier? After all those complications, a small Martian moon can start to look like a very elaborate detour. If the goal is Mars, why spend years learning to live beside it? NASA's human exploration studies have offered a practical answer. A crew could travel into the Mars system, operate near Phobos or Deimos, and develop many of the systems needed for Mars without attempting an immediate surface landing. Under that definition, the first success isn't a boot print. It's proving that people and machines can work that far from Earth for a long time. Think of preparing a ship for an ocean crossing. The harbour isn't the destination, it's where you discover whether the pumps run, the food lasts, and the crew can repair what breaks. A mission near the moons could serve a similar purpose on a much larger scale. Life support would have to keep working throughout a deep space mission. Habitats would need to protect crews for months. Communications would have to cope with long delays. Supplies, maintenance, medical care, and power would all be tested where a quick trip home is no longer available. Then there are the robots. From Earth, a command sent to Mars can take minutes to arrive. A person near Mars could control surface machines with far less delay. That changes the work. A rover could respond quickly when a wheel slips. A robot could collect samples, place equipment, or inspect a future landing area, while nearby people handle the awkward moments that automation still struggles with. Those operations would teach mission planners how humans and robots should divide the work. They could show which jobs need a person nearby, which jobs can be left to software, and which failures require both. They would also reveal how much preparation a surface expedition needs before the crew ever descends. That knowledge can carry forward even if the people gathering it never touch Martian soil. Long-duration presence counts too. Living near Mars would test how crews manage isolation, radiation exposure, limited supplies, equipment aging, and decisions made far beyond immediate help from Earth. It would force ordinary routines to work in an extraordinary place. Meals, repairs, sleep, exercise, medical checks, and the daily business of keeping a small habitat alive. None of that produces a settlement by itself. It does produce experience that cannot be gained during a short stay near home. This is why the argument for Moon First becomes stronger when you change the scorecard. If success means reaching the Martian surface at the earliest possible date, any stop near Phobos or Deimos may look like time added to the schedule. But if success means arriving with life support already proven, robotic teamwork already practiced, and deep space operations already lived rather than simulated, the moons become part of the preparation. The case is stronger than it may have seemed. A moon mission could be a real Mars mission without including a Mars landing, because it would build capability inside the Mars system itself. But precursor value and faster arrival aren't the same claim. One says the work can carry forward, the other says the detour will shorten the road. The trouble is that a hard mission does not automatically teach the right lessons. You can spend years solving a genuine engineering problem, solve it beautifully, and still discover that Mars never asked you to solve it. Imagine training for a long walk by learning to balance on a floating log. Balance is valuable, so is patience, but most of your practice goes into the strange behavior of the log, while the actual walk will punish your feet, your knees, and your ability to carry water. The two challenges overlap, but only partly. Phobos creates that sort of mismatch. Its gravity is so weak that an astronaut would barely feel held down. Moving across it would be less like walking, and more like managing every push. A careless step could send you drifting away from the surface. Tools, anchors, handrails, vehicles, and emergency procedures would all have to work in this very unusual setting. Mars is different. On Mars, you weigh about 38% of what you weigh on Earth. That is weak gravity. but it is enough to keep boots on the ground and dust under them. Crews would need to walk, lift equipment, build shelters, handle pressurized suits, and live for months with their bodies carrying weight. Learning how to touch a tiny moon without bouncing away does not answer those problems. NASA made this concern explicit in a 2021 strategic critique of the moon-first approach. A Phobos mission would introduce systems and risks that a direct surface mission would not require. The crew might need specialized ways to approach the moon, attach to it, move around it, and leave it safely. Each system would need designs, tests, backup procedures, training, and spare parts. None of that work is imaginary. It is simply aimed at Phobos. And engineering attention is finite. So is money. A spacecraft team occupied with ultra-low gravity mobility is not spending those same hours on Mars landing systems. Funding used for moon contact hardware cannot also buy surface habitats, dust-resistant seals, heavy cargo landers, or long-duration tests under Martian conditions. Even when the moon equipment works perfectly, much of it may end its career there. The same problem reaches the crew. Time spent rehearsing how to anchor a boot or restrain a tool near Phobos may be necessary for that mission, but it does little to prepare someone for hauling a damaged rover part across uneven Martian ground, then trying to repair it through stiff gloves while dust works into every joint. Some moon-specific learning would still help. Engineers often find surprises in any real flight, and crews become better at operating far from Earth. But transfer is mixed. The more a precursor resembles the destination, the more naturally its hardware and habits carry forward. Phobos resembles deep space in several important ways. It resembles the Martian surface much less. That is how precursor becomes a detour. The mission succeeds, the check marks fill the page, and the program arrives at Mars carrying excellent tools from the wrong toolbox. So, is going to the moons first smart, or is it a detour? The answer depends on what you want the mission to accomplish. If success means learning to work throughout the Mars system before anyone settles on the planet, moon first makes sense. Crews near Phobos or Deimos could operate equipment around Mars, study the moons, and control machines on the surface with almost no communications delay. They could build experience far from Earth while doing work that cannot be done nearly as well from home. Under that definition, the moons aren't a waiting room, they're part of the destination. But suppose success means getting people safely established on Martian ground as soon as possible. Now the calculation changes. A moon mission needs its own vehicles, procedures, landing systems, surface tools, and crew training. Some of that carries forward, some does not. Every moon-specific system takes money, testing, and time that could have gone toward habitats, power supplies, descent vehicles, and life support designed for Mars itself. Under that definition, going first to a moon can delay the thing the program was created to do. That isn't an attempt to avoid giving an answer. It is the answer. The moons are a stepping stone if Mars system operations, close-range control of surface robots, and moon science are important mission goals. They're a detour if the main goal is the fastest safe path to people living on Mars. Physics can't choose between those goals. It can tell us how much fuel a route needs, how radiation builds up, how long messages take, and what each destination demands from a spacecraft. It can estimate risk and expose a weak design. It cannot decide which result deserves priority. That choice belongs to the people designing the program, funding it, and accepting the consequences when schedules slip. A surprising amount of disagreement about moon-first plans is really a disagreement about that choice. One side sees Mars as a whole region, planet, orbit, moons, robotic fleets and crews, gradually learning to work among them. The other sees a settlement problem. Get people onto the surface, keep them alive, and begin building the systems that let them stay. Both sides can use the same engineering figures and still reach different conclusions because they're aiming at different finish lines. So the roadmap splits cleanly. Choose Mars system capability first, and Phobos or Deimos may earn their place. Choose surface habitation first, and the extra branch has to prove that it saves more risk or time later than it adds now. Being nearby isn't enough. The stop has to serve the destination you chose. Future missions will give us better numbers for that comparison. We may learn that operating near the moons removes hazards we currently underestimate. We may learn that their special hardware costs more than expected and transfers less. Until then, the verdict can remain firm without pretending to be universal. A stepping stone is only a stepping stone if it lies on the road you've chosen. Japan's Martian Moons Exploration Mission, or MMX, is designed to bring part of Phobos back to Earth. Not an image of the surface, not another reading taken from orbit, actual material sealed inside a return capsule and carried across millions of miles. The mission aims to collect more than 10 grams from Phobos. That's a little over 1/3 of an ounce. It also includes sampling from about 2 centimeters below the surface, or roughly 0.8 of an inch. Those amounts may sound modest beside an entire moon, but laboratory instruments don't need a bucketful. A few grains can preserve minerals, chemical ratios, and microscopic structures that no camera can fully read from a distance. Think of the difference between looking at a loaf through a kitchen window and having a crumb in your hand. From outside, you can judge its color and shape. With the crumb, you can test what it contains, how it was heated, and whether different parts formed at different times. Phobos has been observed for decades, but much of what we say about its makeup still comes from reflected light and other remote measurements. A returned sample changes the kind of evidence available. On Earth, researchers can place tiny pieces under several instruments. They can measure elements and isotopes far more precisely than a compact spacecraft usually can. They can search for signs of heating, impact damage, radiation exposure, and contact with material thrown off Mars. They can compare grains from the surface with material collected about 2 centimeters down, where exposure to space may have left a different record. Other laboratories can repeat the work years later. One team can challenge another team's result. Future researchers can return to the same sealed material with instruments that haven't even been built yet. We've seen that happen with samples brought home by earlier missions. The spacecraft completes its trip, but the investigation keeps going. The canister may fit in one hand, while the evidence inside it continues working for generations. That won't tell us, by itself, whether people should live on Phobos or Deimos. A sample cannot design a habitat, price a transport system, or decide how much risk a crew should accept. It cannot tell planners which route deserves funding. Human use remains partly an engineering choice, but the physical facts behind that choice become harder to describe with broad guesses. The returned grains can tighten estimates of what Phobos is made of and how its surface has changed. They may help distinguish between competing ideas about where the moon came from. They can also show what machinery, shielding, seals, and sampling tools would actually meet there, instead of what engineers must currently infer from afar. That doesn't settle the architecture. It gives the architecture firmer ground. MMX turns one of Mars's moons from a remote suspect into a sampled world. More than 10 grams, gathered partly from about 2 centimeters down, could replace whole families of assumptions with material that can be weighed, scanned, heated, split, and checked again. The choice of what humans build will still be ours. Phobos will have supplied better evidence about the world we would be building on. A few grains can do more than add another fact to a shelf. In a laboratory, scientists can use them to sort between histories that currently look almost equally plausible from a distance. Phobos and Deimos may be asteroids that wandered too close to Mars and were captured. Their dark surfaces resemble carbon-rich asteroids, which supports that idea. But capture leaves an awkward problem. An incoming asteroid usually arrives on a stretched, tilted orbit. Both moons now travel on nearly circular paths close to Mars's equator. Getting from one kind of orbit to the other is possible. Explaining exactly how it happened is much harder. The other broad idea begins with a collision. Something large struck young Mars, throwing rock and vapor into orbit. Some of that debris gathered into moons. That can explain the shape and position of their orbits. It also leaves scientists asking why the moons look so dark and asteroid-like from above. A returned sample can test both stories from inside the material. Its minerals, chemical elements, and isotopes may resemble Mars, an asteroid, or a mixture changed by a violent impact. Extreme heat can erase some structures and create others. A collision can leave microscopic signs that even a very good camera in orbit will never see. Under lab light, one measurement after another can remove branches from the Moon's family tree. The same grains can tell us how the surface behaves. Regolith sounds like soil, but it isn't garden dirt. It's broken rock and dust made by impacts, radiation, and long exposure without air or weather. Researchers can measure grain shapes, pore space, strength, electrical behavior, and how easily particles cling to equipment. They can repeat those tests under different conditions instead of relying only on color, brightness, and temperature readings from far away. Those details reduce risk. Fine dust may work into seals or coat sensors. Loose material may shift under a footpad. Electrically charged grains may cause trouble around machinery. Anyone designing equipment for Phobos would rather measure those behaviors than discover them after arrival. A sample won't hand engineers a finished landing system or habitat plan. It can show them which surface assumptions deserve confidence and which ones still need testing. MMX can also read some of the traffic around Mars. Tiny pieces of Martian rock may have reached Phobos after impacts on the planet below. Solar particles and other material moving through the Mars system may be recorded in exposed grains. Mixed together, those traces can help reconstruct how Mars, its moons, and their surroundings changed over time. So the mission can buy something quite specific. It can narrow the Moon's origin, replace remote estimates with measured material properties, and give future planners a more accurate world to reason about. It cannot decide whether people should go there, where they should live, or which machines they should trust with their lives. The science can make the map less blurry. The route across it remains a human choice. A laboratory result can look wonderfully final. There are numbers in tidy columns, labels on sealed containers, and a small piece of another world resting behind glass. After years of guesses from photographs and spectra, someone can finally say what the material is made of. Then you walk into the room where the habitat is being designed, and certainty becomes scarce again. The sample may show how Phobos formed. It may reveal how its surface responds to drilling, anchoring, heat, or dust control. Those answers could remove expensive surprises from a crewed mission. They could rule out bad equipment and give engineers firmer limits. That is real progress. Science has done exactly what we asked of it. But a measured grain of Phobos cannot choose a radiation architecture. It cannot tell us whether a crew should shelter under imported shielding, cover a habitat with local material, or spend more mass on protection carried from Earth. Measurements can show how well each material blocks radiation. They can estimate the dose behind a wall. The acceptable balance between safety, cost, mass, and time still belongs to the people planning the mission. The same boundary appears when astronauts step outside. A sample can warn us that the ground is abrasive, weak, electrically charged, or difficult to grip. It cannot tell us how productive a person will remain after 6 hours in a suit, moving carefully across a tiny moon where every push has to be controlled. Nor can it measure the mental strain of repeating that work for weeks while Mars hangs nearby and home is months away. Those answers need human trials, better suits, operational experience, and a willingness to admit when a plan asks too much of a crew. Even a nearly complete scientific account of the moons would leave the largest choice untouched. Are we trying to build a dependable place for operating throughout the Mars system? Or are we trying to reach the Martian surface and begin permanent settlement as quickly as possible? Those goals overlap, but they aren't identical. A Phobos base could be a strong answer to the first. It might support communications, remote surface work, science, and the gradual learning of how people function far from Earth. If speed to settlement is the priority, every year and every launch spent building around Phobos may look like a delay. No returned sample can rank those aims for us. There is no instrument that measures which future deserves first place. That doesn't weaken the science. Better evidence closes off fantasies, exposes hidden costs, and makes each remaining choice more responsible. It can tell us what is possible, what is dangerous, and what is probably wasteful. That is an enormous amount to know. The final step is smaller in appearance and heavier in consequence. We choose what we are trying to accomplish. If we want a measured foothold in the Mars system, the moons may earn their place. If we want the shortest path to life on Mars, they may not. The rocks can inform the decision. They don't get a vote. Imagine that first base above Mars again. From a distance, it looks like a cautious beginning. A few connected modules sit against the dark surface of Phobos, with Mars filling half the sky. Crews arrive without plunging through an atmosphere. They avoid the first dangerous landing on the planet and the equally difficult climb back into space. From their shelter, they guide machines on Mars without the long delay that comes with controlling them from Earth. Seen that way, living on a Martian moon first is plausible. But the word first carries most of the weight. A base on Phobos or Deimos would make sense if people were sent to work in the Mars system before settling its surface. They could supervise robots, collect material from the moon, test equipment, and learn how human bodies and machines cope so far from Earth. On Phobos, crews might also place part of the moon between themselves and incoming radiation. That wouldn't solve the exposure problem, but it could help. The base would be a command post with bedrooms attached. An odd little workplace, perhaps, but a real one. It would not be a smaller version of a settlement on Mars. The two places ask humans to do different things. Mars makes arrival difficult. Its atmosphere is thick enough to cause trouble during descent, yet too thin to make landing easy. Leaving requires a capable rocket and fuel. Once you are down, though, you have meaningful gravity, broad ground, local materials, and a world where people can walk without drifting away after one careless push. The moons reverse that trade. Reaching them may be simpler than reaching the Martian surface. Daily life would be less natural. Almost every movement, repair, and construction job would have to account for extremely weak gravity. Dust would not settle in the familiar way. Heavy equipment would barely be heavy. Even digging into the surface for protection would become a slow engineering problem when your shovel can push you away from the ground. So the answer is yes. Humans might live on Mars's moons before they live on Mars. Only under a fairly narrow plan. If the first purpose is to operate near Mars, study its moons, and prepare the planet through robotic work, a moon base has a clear role. If the purpose is to place people on Martian ground as soon as practical, stopping above the planet may add another habitat, another transport system, and another place where everything must be kept alive. Japan's Martian Moons exploration mission may change what engineers know about Phobos and its material. Later work on radiation protection, life support, and transport may shift the balance as well. Better measurements can tell us what each route demands. They cannot decide what people want the first crews to accomplish. That choice comes before the base. Perhaps the first human home in the Mars system will stand on the planet, surrounded by rust-colored ground. Or perhaps it will cling to a small moon overhead, close enough for Mars to dominate every window, while robots do the walking below. Both futures are possible, they just mean different things. A moon base says we have come to work near Mars before committing to life upon it. A surface base says the difficult landing was worth making, because the ground itself was always the destination. So yes, we may live on Phobos or Deimos before Mars. But only if being above Mars is useful enough to delay being there.